In the second part on light, we're going to talk about how light comes from different types of bodies, in particular solid or high-density gas bodies, and this will introduce us to black bodies. So how is light made? Well, basically all objects emit light. You and I are emitting light according to our temperature, which is 310 Kelvin, 37 Celsius, or about 100 Fahrenheit. And as you cool things down, they give off less energy and at different wavelengths, but everything gives off energy. This is how we use night vision goggles, and this is how we get to detect objects in space. But let's just do a little bit of a thought experiment on this. So I want to think about an iron bar. We've got an iron bar. It's cast iron, it's almost black, it's at room temperature. So it's black. It's glowing in the infrared because it's at room temperature, so it's about 300 Kelvin. Now we're going to heat it up. What happens first? Well, the first thing is it's going to start glowing red. It's glowing red and it's kind of a dull red. As we heat it more, what happens? Well, it's going to glow a little brighter and a little more orange, and then a little brighter and a little more yellow, and we keep heating it, and it's going to get brighter still and white, and assuming that it doesn't just melt, it'll get brighter still and go a little blue. What is it that we're actually seeing? Well, we're seeing it go from blackish to red to orange to yellow to white. At the same time, it's going from blackish to a dull glow to a bit brighter to brightest. Now, in each case, we understand that it's a hotter temperature. At a higher temperature, we have shorter wavelengths. At shorter wavelengths, we have more energy. But also at a higher temperature, we're seeing it brighter. We're getting more photons. Now, before we can move on, I just want to make sure that we understand what we mean by temperature. So what is temperature? Well, temperature is really just a measure of how fast atoms are moving. We will come back to this because it's really important for how we understand all sorts of things in space. But basically, you've got different scales. And in the US, most people tend to think in Fahrenheit. We tend to think of our body temperatures, of the temperature of the air outside, for cooking in Fahrenheit. In most of Europe, people tend to think in Celsius. Fahrenheit came up with his scale, understanding that the bottom of the scale was not zero, that was not the freezing point of water. So he set the freezing point of water at some arbitrary point. And then he said, okay, I need to have the boiling point of water at some number above that. And he chose 180 because at that point, people weren't really into decimals. And a number like 180 is good because you can divide by 2, 3, 5, 6, 9, 12, and so on. And so it was a nice number to play with. And so that was how that scale got set up. It was basically using water as its scale. And then Celsius came along and said, well, that's a really complicated scale and it's kind of arbitrary. So let's just say we know that you can go below freezing, so let's just have negative numbers for below freezing of water. Let's make the boiling point of water of 100 and scale accordingly. And then Kelvin came along and said, I know what zero is. Zero is when atoms no longer move. And so what we have is, he took the Celsius scale because there were lots of things that were already calibrated for the Celsius scale. And he said, I'm going to work out, based on the Celsius scale, at what temperature does stuff stop moving. So as you cool it down, the atoms move slower and slower, and slower and slower, until eventually they stop. And they stop at minus 273 Celsius. So he said, okay, I'm going to make that zero, but I'm going to use the Celsius size. So the freezing point of water is 273, and so on. And you can see here that once you get up to higher temperatures, you start to not worry about the difference between Kelvin and Celsius, especially once you get up to the sort of temperatures inside of stars. Now, I want to share a little bit of an anecdote that I came across probably almost a decade ago. John Madden was doing Monday Night Football, and there was a game on in Chicago, and the previous week it had been on in Phoenix, it had been on in Arizona. And so he said that the temperature in Chicago at this game we're at today is half the temperature we had in the game last week. Why is that not true? So this was a September game, it was in Arizona, and it was 80 degrees. Whereas a week later in Chicago, it was only 40 degrees in Fahrenheit. But that's not half the temperature. Half the temperature is really a measure of half the speed of the atoms. So what is the temperature of half of the 80 degrees Fahrenheit in Arizona? Well, we have to convert first. So if you want to convert to Celsius, you times by 5, divide by 9, and subtract 32. So 80 degrees Fahrenheit is 27 degrees Celsius. And then we want to make it into Kelvin, so we just add on 273, and we get that the temperature in Arizona, when it was 80 degrees Fahrenheit, is 300 Kelvin. So half the temperature in Arizona is only 150 Kelvin, which is pretty cold. If you convert it to Celsius, we're down at minus 123, and if we convert it to Fahrenheit, we're at minus 189 degrees Fahrenheit. That's not just cold. It's unheard of on Earth. And in fact, that's cold for Mars. Even on Mars does experience temperatures like that, but that's a cold day on Mars. And so I like this as an example of how you need to be careful about what units you're using. And scientists like to use either Celsius or Kelvin, and physicists and astronomers generally use Kelvin. Geologists like Celsius because they're weird. Anyway, and just to put it in context, the temperature on Mars is about, the average temperature is about minus 81. So it really is a cold day on Mars. Okay, now let's come to the idea of blackbody radiation. If you should have come across this a little in university physics, and it should be in Intro to Modern. But basically, if we take the spectrum of a star, that is, we spread out its light into its individual colors, we find that it behaves more or less like a black body. What does that mean? Well, a black body is something that glows only according to its temperature. It doesn't reflect any light. We all reflect light. You can't see me right now, but if I'm wearing a yellow t-shirt, then I'm reflecting a lot of yellow light. And lots of people at Mizzou wear yellow. But you can use the black body radiation. All light that falls on it is absorbed, and the emission of the light is only from the temperature. But it does it in a very predictable way, and so if we spread it out, and so here I've got graphs, this is the wavelength in nanometers on the x-axis, and the brightness on the y-axis, and you can see here I've got visual light, I've got ultraviolet, I've got infrared, and this is using temperatures that are relevant for stars. I've got a 5,000 Kelvin black body, a 6,000 Kelvin black body, a 7,000 Kelvin black body, and I have here this curve, and you can see how the light is distributed. At 5,000 Kelvin, I have more red light than blue light, but the peak is somewhere around orange. If I go up to 6,000 Kelvin, which is approximately the temperature of the sun, I have more green light than anything else. I have less blue light and even less red light, but the color that my star will appear is the combination of all of these, so it tends to be kind of yellowish white. If I go to 7,000 Kelvin, I've now got more blue light than red light, but I still have all of these colors, so as you mix them together, it'll be a bluish white. And down here, where you've got more red light than blue light, it's going to be a orangish, reddish color. And so this is how we compare these in terms of thinking about the iron bar and heating it up. As it heats up, you go from something that is reddish to something that is yellowish to something that is whitish. Now I just want to consider lava for a minute, because we know that lava glows. In fact, I'm married to someone who plays with lava in his lab, if you ever want to see any. You might think that it's something that it's generally reddish, and so maybe it's up at 5,000 Kelvin. Is that really the temperature that it's at? Can we tell from how it's glowing? Well, we can actually tell by looking at where it peaks, and this brings us to Wien's law. So here we've got the distribution of light. So here I've got a 12,000 Kelvin, a 6,000 Kelvin, and a 3,000 Kelvin. And you can see here, at 12,000 Kelvin, it's actually peaking in the ultraviolet, but it's giving off more blue than red, but you still get all of these colors, so it's going to be bluish. We've got at 6,000 Kelvin, it's peaking right around green, but it's giving off all of these colors, it's going to be yellowish. And here, at 3,000 Kelvin, it's actually peaking in the infrared. It's giving off more red than blue, so it's going to be reddish, but it's going to be pale because you have all of those colors. And actually lava depends on actually the composition of lava, but it's typically somewhere in the 1,000 to 1,500 Kelvin, and so it would actually peak right around here. But what you get when you think about it, if you shift this curve is always the same shape. This is a log scale, so as you move this across, as you have it drop off, you basically don't have very much blue light, and you'll have some red, and so it's going to look reddish because they're the only photons that you really receive. At 4,000 Kelvin, it peaks in red light, but it's giving enough of the other colors that it's actually going to be kind of orange. And so you can see here how it peaks at 5500, it peaks in yellow light. At 7500 it peaks in blue light, but you're still getting a lot of those other colors, so they tend to look different colors. So actually at 2000, 3000 Kelvin they look red, 4500 they look orange, at 6000 they look yellow, at 10,000 they look white, and it's not until they get up to really high temperatures that they're going to look bluish. Now that was Wien's law. Actually, let me just back up. That was Wien's law. This is basically explaining how we've got a maximum wavelength. So here we've got the peak of this curve is here, the peak of the curve is here, the peak of the curve is here, is a simple relationship between the wavelength of that peak and the temperature. If the temperature is in Kelvin, then this gives you the peak in microns. So at just under 3000 Kelvin, it's going to peak at 1000. If it's 6000 Kelvin, it's going to peak at about 500, and so on. And so this allows you to do a quick estimate of where it should be, but it also allows us to do some interesting stuff with stars, which we'll get to later. Now, there's another law that relates to black bodies and how they emit light. So we already saw in our thought experiment that as we heat up the iron bar, not only does it change color, but it emits more light. And so we have more energy in the atoms and they can radiate more. And what you get is that the flux, that is the amount of energy per second per unit surface area, is proportional to the temperature to the fourth. And remember, this is the amount of energy passing through a surface per second, and so it matters how big the object is, and it matters what temperature it is. And so you can make, you just need a constant. This is the Stefan-Boltzmann constant. It's one of the few that I can remember because it's 5.67 times 10 to the minus 8, and so it's 5678. So this brings us to luminosity. So luminosity is the total amount of brightness that something gives off. So we've got flux, which is the amount of energy per unit surface area, but that means if we know what the surface area is, we can multiply the flux by the surface area and get the total amount of energy per second being emitted. And so for a sphere, a lot of objects in space can be simplified to spheres. We have the surface area, which is 4 pi r squared, times sigma t to the 4. So this gives us a relationship for a star between its luminosity, its radius, and its temperature. And so for energy output, at a given temperature, you're going to have a certain amount of energy given out. And the total energy is basically the area under the curve. Here I've got them plotted in, this is in frequency space, so this is the brightness and the frequency space, and this is the brightness and the wavelength space. And you can see that it gives off lots of energy, and it's the area under the curve that gives you the total amount of energy. It's basically, I've got this much energy at this wavelength, and 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 so on. If you add all of those up, you get the total amount out. According to the Stefan-Boltzmann law, if your objects are the same size, then they will give off much more energy if they are hotter than if they are cooler. And that brings us to the idea of an effective temperature. So the effective temperature is the temperature that a body has if it has a given luminosity and a given radius. So basically what this is saying is that you have L equals 4 pi r squared sigma t to the 4. If you know what its luminosity is, how much energy is it giving off, and you know what size it is, you've got an effective temperature. If it's a black body, it should be the same. It should be that the effective temperature is the same as the brightness temperature. And the brightness temperature, it really is just the temperature of a black body. The color temperature is, if you've got something, where is the peak brightness? The peak brightness gives you lambda max, and lambda max gives you a temperature. Most things are not perfect black bodies, so usually the effective temperature does not quite equal the color temperature. And for astronomy, that can be important for understanding how they don't behave quite like a black body. And next we'll move on to how light interacts with things that aren't solid or high density gases.